Hey, yay. So we're back again. Are you able to hear me like this? Is this okay? Or is this
Oh, you're on a call?
no, is this audio okay? Like is this
Yeah.
this audio level? Okay, sure. So it's the same whiteboard as usual. I'll just drop the link. Okay.
Yeah. Okie dokie. Cool. Yeah, I'm getting in soon.
Sure.
I was thinking of doing some like very basic homology today because why not?
Oh, okay. Cool, sure. So
I'm
today,
heading to something I don't know. I don't know exactly what I'm heading to, but I'm
mhm.
getting there. Like yeah.
Cool,
Uh,
cool. Co-homology besides the standard DRAM, there's also I've been trying to study
Singular?
the
Oh,
check
Sesh.
co-homology.
Yeah.
Sesh. I'm not sure how to pronounce it. Is it
Yeah.
Sesh? Okay,
Uh,
sure.
I mean,
Um,
uh, I say sesh. The thing is,
okay.
I self study a lot, like you. So a lot of the time, when you self study, and if you haven't seen any like video lectures, you pronounce things quite weird because you've only read them.
Yeah, yeah, exactly. I've always in my mind it's always been check.
Hmm.
Oh, it looks like I put I put the head on the wrong place. It's on the C. It's
Yeah,
quite
I
it's
also
quite
want to study this.
yeah, it's quite miraculous, or rather it feels like okay, there's singular cohomology,
Yeah,
and then there's check sesh. I'll just call it sesh.
and
Uh
then there's
it
also
seems
Morse, which
oh
is
yeah,
a
yeah.
bit more niche, but it is cool.
I have heard of Morse theory, but I haven't heard of Morse cohomology. Um,
Yeah, it's just like a standard topic, I guess, in Moore's theory. I don't know, but like, yeah,
I'm not sure if DRAM and singular are specific cases of sesh. Uh,
yeah, me neither.
because
I'll have,
it sounds like the sesh cohomology is really really general, because they talk about they define things in terms of um
sheaves.
pre-sheaves and functors, and generally speaking, that just means allocating to each coordinate chart some
Yeah,
structure. So attaching up here could be a group, it could be I don't know, it could be a function, and that seems like it captures a lot of generality to me.
yeah. Hmm.
And it's
Maybe
also
I
quite
don't know.
amazing how
Maybe
yeah,
about
go on, go on.
3 or 4 weeks later, um, I'll be talking about sheaves and then maybe schemes or whatever because I think that's interesting.
Yeah, sure. And the restriction morphism and stuff is quite I still haven't fully understood it. Oh, the reason why I'm studying Sesh homology is because Edward Witten's paper on the chiral DRAM
Oh,
operators, right?
yeah,
It he essentially the DRAM the chiral differential operators, they uh it's essentially he in BRC cohomology,
yeah.
um oh yeah, BRC cohomology is another one. He kind of I think he uses that and he relates it to Sesh, and
Huh. That's
yeah, so he
cool.
did mention Sesh cohomology. It's like the way that he um okay, let me try and recall. The last time I left off, I remember this beta gamma ghost system, and that's for the case where your target space is so in the case where the target space is S1, right? Your
Yeah.
target space is S1, then he covers it with two maps that overlap in the so there's northern
Is it
hemisphere, and then there's
S2
southern.
or S1?
Oh yeah, sorry, S2. And then the southern hemisphere, and then he mentions that some gluing compatibility relation in between here, just like the normal. Usually we do z 1/z.
Yeah.
Z prime is 1/z. But then I think this gluing would affect the ghost or something. And how you glue it is basically Slash code homology is concerned with how you glue different pieces,
Yeah.
different structures when they overlap, the gluing relation in between. Yeah. So yeah, still have to study it.
Yeah, it seems interesting. I hope I can get to something similar like that, but right now I'm kind of um working on the basic mathematical foundations to do physics in a more rigorous way.
Sure, sure.
But today is cohomology day because like in this video I'm a bit tired today, so I'm going to do something very easy, and I'm just going to like explain the very intuitive first principles of cohomology.
Sure,
Um,
sure.
so I let me write. Well, I'm just gonna do homology today. But first, I'm gonna talk about homotopy, or homotopy. I don't really know how to pronounce it, but like, so basically, it's when, for example, if you have like a line, if you have a curve with fixed endpoints, a
Mm,
homotopy is when if you like you create like you move this line, you move this curve, so that like every point basically goes on a continuous trajectory as you move it.
mm,
So two curves are said to be equivalent if you can move one curve and deform it into the second. So, for example, if you have like just ordinary space, then these two would be homotopically equivalent. But if you have a space where it's basically, so this is just ordinary space. But if you have space that's basically ordinary space excluding the origin, then there is no origin, so you can't cross through it. So this point is not going to be equal to this. Because
mm.
if you try to pass through, you'll see that there's a problem because you can't really go through the origin because the origin has been left out. And so that's homotopy. So similarly, we have homology, which is a bit different. So in homology, if you have some kind of curve, this curve is basically equivalent to some other curve. So wait, before I talk about equivalences, let me talk about the ways I can change this curve. So what I can do is I can come up with a region. So this is a 1D curve, but I can come up with a 2D region, one that looks like so. And then I can take the boundary of this region, which is denoted using this interesting symbol. It will look like
Mm,
this. And then we can talk about the resulting curve, which is basically the original curve plus this new curve. We see that these two are homologously equivalent if there's like basically they differ by the boundary of a two-dimensional region, two-dimensional shape.
mm.
Um,
Yes. In other words, suppose we have R2 minus the origin, then
yes.
the curve of A is
Yeah.
homologous to the curve of B,
Yeah.
but it's not homologous to, so A and B are
I think
equivalent.
it is homologous to C, I think.
Oh, it is?
It
I'm not
is,
sure. Okay.
right? Because
But
like
then there's
um if you like take this region, uh
mhm.
like B plus C is equal to partial of this thing. So they
Oh,
are
I see.
homologous. Yeah.
Uh, okay. Then could you come up with an example because I think I've been a bit confused.
Yeah, I would say that these two are homologous. S- uh I mean like obviously like let's say like you can consider basically some region containing the origin, but obviously not including the origin. But if you were to
Mm,
take the boundary of this region, I would expect that is just this outer part. Uh,
mm. Oh, but is it the outer part plus the inner part? So you look
Is
something like
is there?
not sure.
but like the boundary should be
Oh,
included in the original space, and the origin is not in the original space. I think this is a bit I
oh,
think this
right,
is
right.
slightly confusing and nitpicky. I'll have to
Mm,
like cover this in like a later uh
sure, sure.
video because I don't really know right now.
Mm,
In this video, I'm just gonna talk about manifolds with boundaries, which is
okay.
okay. So the original definition of a manifold, basically, is covered by patches that are So I'm either going to talk about compact manifolds, which are basically don't really have these kind of like open boundaries.
Mm,
So if you were so the reason why so a compact manifold basically contains all its limit points. And what I mean by that is if you were to consider a manifold that looks like this, which has like an open boundary, um, you could take a sequence of points that converge to some point on the boundary, but you're not including the boundary. So that point is a limit point that is not included in the original manifold. So this is not
mm,
compact. So all compact manifolds basically uh, have to have no boundary, because technically speaking, manifolds with boundary um, are not manifolds. Because if
mm,
you take a point on the boundary, then locally there is no patch
mm,
containing that point so that it maps to the point inside an open set of Euclidean space.
right.
So compact manifolds don't have a boundary, but you can define manifolds with boundary, which is not a manifold,
Mm,
which is basically like these with the boundary included. Just saying. So we're going to consider these
okay.
twos in today's video. I hope that yeah, so we're not going to talk about the ones with the unincluded boundary.
Mm, sounds good.
Yeah. Oh, but anyway, so I want to mention something about like the formal sum of curves. So like we're going to take every curve to like curve in every shape to have an orientation. So basically for one dimension, this is like basically we're going to define that if you have some curve like this, then it is -1 times the curve, but in the opposite direction. So there's like a
Mm-hmm.
directionality to it. Um,
Mm,
and for two-dimensional shapes, if you intuitively think about three-dimensional geometry, then every two-dimensional space has like two normal directions. So this is a bit
mm,
similar to that. Um, uh, One way to think about it is, I guess, you could have like this kind of you could draw this kind of like rotation inside the two-dimensional shape, and if you do the minus that, it's like in the opposite rotation. So basically, if you have a two-dimensional shape, you can, if it is orientable, you can continuously like draw these types of like swirls inside the shape,
mm,
and you will either have one of two cases where all the swirls are basically pointing in the counterclockwise direction, and where all the swirls are basically pointing in the clockwise direction. And these two are considered
mm,
to be opposite orientations. Um,
mm,
the mathematically rigorous way to state this is basically you define a two-form field, a non-zero two-form field omega on the 2D manifold, and you'd say that these two-form fields, we define an equivalence relation on two-form fields so that basically if you multiply a non-zero, non-zero positive scalar field, we consider them to be equivalent. So this is like an equivalence relation. We can see that basically the non-zero two-form films fields split into two equivalence classes, which are the two orientations.
mm,
And like this obviously generalizes to higher dimensions. So that's how I define orientations. I think different people have different ways to define orientations. But I personally like to define orientations as equivalence classes of non-zero D-form fields on a D-dimensional manifold.
Sure.
So the formal sum thing. And this plus itself is just like to the curve. This is kind of abstract because it is, and obviously this minus itself is 0, so on and so forth. So we have this idea of like a vector space of curves and like some kind of reasonable intuitive way of defining addition to them. So if curve A, you want to say something?
No.
So if curve A is homologous to curve B, then if we calculate A minus B, it should be equal to the partial of some C, where this is plus 1 dim compared to A and B. So but here's another interesting thing. If you take, for example, this, and we can like do this further. So okay, so here's an interesting thing. If you take this two-dimensional region called S, if you take partial S, it's just going to be this circle. If you take the partial of partial S, it's not going to be existent. Here, basically, the boundary of a curve is basically equal to its 2 points. But the boundary of a closed curve is non-existent. And we see that basically boundary squared is boundary. This is always 0, which is interesting. And it's actually, yeah, it's pretty interesting. And
Well, I think one way we can elaborate on this part is that the circle can be thought of as having a certain direction to it. So
yeah,
this thing with a direction to it is equals to this curve
yeah.
plus this curve.
Oh,
And when
yeah,
you add the two curves together, you can think of it as this curve minus this curve, and
yeah.
then you compute the boundary of this curve
Right.
minus
Oh,
this curve,
yeah.
and you get the same thing. Yeah, you get
So, one thing that I have to point out is that if you have these like dots, technically speaking, the boundary of this thing. Oh, so like, yeah, you need to consider orientations when taking boundary. Okay, so like if you,
right.
so
So if
dots
you
have two orientations. They have a plus orientation and a minus orientation, which is kind of obvious. So if you have like a curve, then if we take the partial of that, we define that basically this gives the dots an orientation of minus and plus. And
yeah.
if we have a counterclockwise oriented surface, then the boundary of this is taken to have this type of orientation on the resulting curve. And we can actually do this to like three-dimensional ones. So one way to do it is if you have like a cube like so, and the orientation is 1, 2, 3 orientation. Basically these are all equal to 2, 3, 1, 3, 1, 2 orientation, which is equal to minus 1, 3, 2, 3, 2, 1, and 2, 1, 3 orientation. Then basically if you take the partial, this results in, if I recall correctly, this results in the rotation as follows.
Let me think. Yeah.
Right. The formula for
Yeah,
this
correct.
is that if you have something, right? If you have something, then you can think of the orientation as like a D form, right? So there's omega. But on the boundary, there's the orientation. This is omega D. But the boundary, there's orientation omega D minus 1. And then you have like a vector that's pointing outward, right? It doesn't necessarily have to be normal. It just has to point outward, a vector. You can define this even if there isn't a metric, which we will call n. The rule here, I think, is that omega d minus 1 is like defined to be I n omega d. If you're not used to this notation, it basically means if you write it out at indices, omega d minus 1, we can write it using indices a1 to ad minus 1. This is equal to omega d a1 ad minus 1, and then you do the contraction of indices with this n vector. This is like the general definition of like the orientation induced on the boundary of a higher dimensional thing. But like in the cube case, for example, the orientation up here was basically 1, 2, 3, or in other words, 3, 2, 1. No, not 3, 2, 1, but 3, 1, 2. And up here, basically the outwards vector, you can think of it as being 3. So basically, if you take 3, 1, 2, and you contract this with 3, you get 1, 2. So the orientation on the surface here is 1, 2, which would be in this direction. Yeah, and this is important because you can argue, hey, why can't we just put a minus sign there? You can, but like this is the orientation that goes into Stokes' theorem. So it's good if you know this. But anyway, yeah. So I guess there's multiple ways you can see it. As Chanel mentioned, you can even think of it as follows. If you have a circle like this, you can think of it as basically a curve that has the same endpoint and start point. So if you take the partial of this, you would get plus, and you would get the plus point and the minus point. So obviously this will be 0.
Yeah.
But anyway, yeah. So the interesting thing is sometimes it's kind of fun to ask the question of, are there any curves that satisfy partial x is 0, but x is not partial of y? Now this is a hard question. So for the people in the audience who have 0 mathematical background, I encourage you to right now pause the video and try to think of an answer to the following question. Can you find curves that satisfy this in R2? So you can pause the video and think for yourself if those exist. And if you've stopped pausing the video and you found out that indeed there aren't any curves, then you'd be right, and this is due to the Poincaré lemma. But yeah, if you try to look for a curve in R2 that basically if you try to look for a curve in R2 that basically satisfies having no boundary, well, this can't be it. So it should only look like this, or maybe this. But these guys are all basically the boundaries of some two-dimensional region. So you'll see that we can't really find anything satisfying this relation up here. But the thing is, if we go to the torus, then things become different. Because on the torus, you can find some curve x that satisfies having no boundary, but not being the boundary of something. There's actually 2. And the first one looks like this, and the second one looks like this. And you can see that they are not homologous to each other, which is interesting. So you can see that finding these types of curves can help you determine what kind of space you're living in different topological spaces. Have like different types of these particular curves. Okay, let me give some more examples because this is interesting. If you were to say, you can think of like more examples. Another example of a curve like so on the torus would be, this is kind of not very easy to draw, but basically one that basically wraps around the torus once as it like goes around the torus. And you can actually check that this this yellow one, this orange one is equal to the green one plus the violet one. To prove this, let me just draw another shape. So you have the violet one like so, and you have the green one like so. You can add these together in some way. You can see that we can homologously deform the sum of these two, into basically the following curve. And then you follow the green one downwards, then you go here, and then you just slowly deform into orange. So you can see that we can get the orange one by adding, the orange one is homologous to the sum of these two. And so you can actually prove that the space, the vex space of curves satisfying partial x partial x is 0, but x is not partial y on torus is finite dimensional, is two-dimensional. And this is called, was the index up or down for homology?
I think it's down.
Okay,
yeah,
cool.
I think it's down.
This is called H1 of the torus. So this is actually a group, which is because this is actually an abelian group, and it's called the first homology group of the torus. And I think this will be very cool. And now I'm going to talk about relative homology because it's also important. Wait, I like the thicker lines more. Okay, so the relative homology is basically when, let's see here, let me give an example. A good example for this is the annulus. So I'm going to consider a region that looks like this. This is a two-dimensional region, which I'm going to call A. And we have, in this region, we have this one-dimensional region, which I'm going to call B, which is basically just the inner boundary and the outer boundary.
Sure.
And we can define the relative homology of A with respect to B. So I'm trying to do something called H1A comma B, which is defined as follows. So, okay, first, we're going to say that two curves, x and y, are homologous if basically x minus y is equal to the boundary of something plus a remaining part, which is in B. Well, not in, yeah, which is in B. So let me give an example to this. We're going to draw the two curves. This is going to be x, and this is going to be y. If this was just ordinary homology, then x and y would not be homologous, right? Because together they do not form the boundary of some region, but now they do. Because we can consider this region here, and this is w, and we see that x minus y plus w, or basically the orientations like so, is equal to the partial of something over here, which we're going to call z, so partial z. So yeah, so in relative homology, we're basically like, we basically have this new added rule regarding these. So yeah. And let's see if there were any other rules.
So what would be the relative homology of A and B in this case? Because I'm not super familiar with.
Yeah, I'm getting there. So we're going to look for curves that satisfy partial x in B, but x naught some partial z plus w, which is in B. And we see that in this case, so this is basically, this becomes H1A and B. So we're basically looking within all the curves that only have a boundary component in the B region. So they would look like this or this or this. So within all these curves, we're looking for the ones that do not form the boundary of some two-dimensional region. Oh yeah, over there, yeah, thanks. With some boundary region. So like these two cannot be included because they form a boundary of these regions if you include some region in the B region. So you can't have that. But like this one is good. So you can see, so this one is in H1. And we can see that there are two, basically, if you can find the basis for the vector space of H1, which is this and this, these two. Downwards, thank you. A bit more down.
Oh, I see.
Yeah. So these two
Okay,
basically span the vectors.
I see. Okay. So one of them kind of goes directly, and then
Yeah.
one of them goes like kind of one round like this. Is that right?
Yeah. Yeah, but
Okay.
or you can consider one like this and the other one like this.
Oh, I see. It's equivalent. I mean, they're sums of each
Yeah.
other. But the boundary of the second one over here, what would be the
Yeah.
boundary of this? Is just zero, right? Is zero part of B, I guess. Zero
Yeah.
is
Yeah.
the
0 is in B. Right. Yeah. Yeah.
okay. That makes sense. Yeah.
The boundary has to be either 0 or just in B. Like,
Sure.
and there are a few things that are interesting in this case. There are some things you can consider, which is actually a bit interesting. So, okay, here's the fun part, actually. Let's see. Okay, so we can do some additional fun stuff. We can do something. We can actually try. We can actually see. We can try something. This is what we're going to do. We're going to try and calculate H1, and then we have like A and B. Or we're going to try and calculate something like this. Here, the backslash basically means take B minus basically the B cup U. So if you have B, and if U is a region in B, then like the rest is B backslash U. So we're going to calculate this, and there's going to be something very interesting here. Well, not entirely interesting, but like whatever. And like we're going to see that basically, if you have A and B here, let's take, for example, we're going to take U to be something like this, just for fun. Like this is U, and so, or maybe like something, yeah. Okay. Wait, I'm not sure if this is a good idea. Okay, maybe we should just do U being this. Okay. So in this case, we're to calculate H1 of a U and B slash U. This would be this and dot, 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 like this. This is one of those weird
Mm.
examples, but hopefully we can make some sense out of it. So in this case, if we look for the elements in this, obviously there's this one.
Mhm.
Right, because where is it? Yeah, I don't wait, let me just pause the video for a while and go see the definition.
Okay, let me I shall pause.
So yeah. Uh let's see, let me use my common sense. Um uh I guess I've like only seen like the definitions of like homology for like manifolds with boundary or compact manifolds. But in the case where there's like when the manifold basically looks like this, it gets a little confusing. To say if this thing is homologous to zero or not. Because if you take this region, I'm not
Mm.
sure if you could say that if you have X and this is S, then X is boundary of S. But something about my intuition is telling me that it's not.
Mhm.
Um, something. My spider sense is telling me that um the correct mathematical definition of partial S in this case. Obviously, I could be wrong because I'm not really quoting anything. But my spider sense is telling me that this should be equal to X plus like the interior part, even though it's not included in the original manifold. I think
Mm.
I think that's the right way to define things. I'm not sure. I could be totally wrong, but like let's just assume that it is just for today's video. So like in this case, we see that basically we have two guys in the relative homology group, which is basically this guy and this guy.
Mm.
Um, yeah. Um, and so we actually see that like these two are isomorphic. And if I recall correctly, there was a theorem that we can do. This leads to a theorem where basically if the closure of U is contained in the interior of A, then this isomorphism exists.
I see. So it's a theorem?
Yeah, apparently. Like I'm still learning this, but like yeah.
Mm. Cool, cool.
And then there's like one more thing that might be interesting. Um, let's see here. Okay. And there is also another thing that we can consider, um, which is I'm going to explain right now. There is another thing we can consider. We're now going to consider H1 of X and A and just X H1 of A. And let's see. So for the previous case, what we have here is basically this guy, and over here. well, we'll have two things that are not homologously the same. We have this one, and we have this one too. These two are actually not the same.
Right.
There is. Could you pause the video for a sec? I gotta search this.
Sure.
Okay, so are we good?
Mm.
Okay, yeah.
Yep.
So let me just consider something else for a sec. Let me not consider H1, but H0. And if you think about it, H0 is just the total number of
Of connected components.
yeah,
Path connected components.
of path connected components. So we have here is this. So we have one here. We have two here. We see that there is a map, which I'm going to. This might be confusing, but I'm also going to write it this way. So basically, what we do here, yeah, we're literally just like mapping each curve in here to the boundary. So this maps to 0, and this maps to 1 plus 2. So we see that it is not an isomorphism, but it's not an isomorphism, but it is a map, and it's a linear map. We see that there is a linear map from generally speaking, hn plus 1 of x and a to hn of a, which is called the boundary map.
I see.
Um,
I see that in
and that,
Wikipedia, they define in terms of like they define in terms of the short exact sequences and quotient. Yeah.
yeah,
Just wondering uh if there's any quotient kind of thing over here. But are we
with
not
the
gonna touch the quotient?
yeah. Um, well, I mean, with the boundary map or quotient,
As in, I just see that on Wikipedia, the way they defined it, it involves quotienting the chains or something along that.
yeah,
Quotienting the
yeah.
yeah, the chain.
That's
Uh,
pretty much what I said, I think. I
I
just
see.
said the whole quotient thing, but in an intuitive way. Um,
Hmm. This from Hn plus one to Hn,
yeah.
basically. I
So
see.
I'm just gonna randomly talk about quantum error correction, but because this is related to quantum error correction. Um,
Oh wow, that's wow.
but I'm gonna be very brief. So quantum error correction. So I'm in a quantum error correction. I'm in a quantum information theory class right now. But I'm not
Oh
really
cool.
interested in building quantum computers right now. So I was just wondering what type of math they're doing. And I kind of realized
Mm,
that you could if you're not interested in building quantum computers, but you still want to know whatever the people over there are doing, this is how you can just really understand quantum error correction is so. So you have a small Hilbert space, you have a k-dimensional Hilbert space, and you have a d-dimensional Hilbert space. D is bigger than k,
mm.
and there's just some map. Um, there's just some isomorphism. But there's
Wait,
also a map
but
from
two,
HK
is
to
it
like a k-dimensional
four?
subspace.
Oh, okay, sure. Yeah.
But like if you think about it, like yeah, that is like a quantum that is called a quantum error correcting code. That's called a quantum error correcting code.
Mm,
And the reason why it's called an error correcting code is like it tends to like save your information from like local errors. For example, if you have like 0 and 1, so this is like a 2 dim, so k is 2. If you have like the case where k is 2 and d is, oh, actually this is like 2 to the k and 2 to the d. I think this is how to talk about it. Um, because it's like with bits and
right,
stuff
right.
like that. So
How
like
many qubits?
in the case where k is 1 and d is like 3, you map like
Mhm.
0 to 0, 0, 0 and 1 to 1, 1, 1. the cool thing is that if there's an error and like 000 gets flipped to 100, you can see that, oh, there's two zeros. So this should have been 000 and stuff like that. You can fix the errors.
Yeah.
Yeah, that's pretty much it. But yeah.
Oh, I see. But how is that
So
related to relative homology?
so yeah, the cool thing is like how to define your two k-dimensional subspace, which is called the code subspace. So you can define it you can use this formalism of stabilizers, which is a lot of jargon for really not much of anything. But like, so basically the stabilizers, so you have some kind of abelian group of operators. So they have to commute with each other.
Okay.
And this is a finite abelian group. Well, not well, yeah, it's finite. I think so. Yeah, it is. Okay, so of operators, and if I recall correctly, these have to be yeah. These operators are like usually like Pauli operators, if I recall correctly. They're like Pauli, so like if you have like a three-qubit system, then it's gonna be like Pauli x like xz or like xzz or whatever, those types of things, like usually I think so. Like these operators tend to they usually like either commute or anti-commute with each other, but in this case you have to
I see.
select a bunch of ones that all commute with each other, and they either have eigenvalues of +1 or -1.
I see.
So
XXZ meaning XX on the first qubits, XX on the second qubit, and ZX
yeah,
on the third qubit. Okay.
yeah. So basically, you have these. So this if you call this G, then you can write G as basically being generated by a finite number of group elements, and like the rest of the group elements are just made by like multiplying these together. Um, the stabilizer, the code subspace is basically defined by the space of ket satisfying G1 phi equals 0 dot 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 G M phi equals 0. Um, yeah. And, oh, not just this, but like all the things. Um, um, yeah, that this is it. So like this. So basically, if you act like any operator in the stabilizer group, on the ket, it would no, it's not 0. It's not 0. Sorry, it's the original ket. So was it
I
0?
see.
Oh yeah, it's 0. Oh, is it? Oh god, I'm so confused. Wait.
It's okay.
If I recall correctly, I think this was just wait, was it? God, I'm so confused. It was 0. It was 0. Yeah, it was 0.
I
Yeah.
see.
Um.
So the uh, I see. Is the finite abelian group in this case? So I still don't see the exact link to
Yeah, we're getting there.
error
We're
correct.
we're
Oh,
we're,
okay,
we're,
sure,
we're
sure,
getting there.
sure, sure. Okay.
Let's see here. Just a second. Uh. So. Okay, just stabilizers. Wait, I keep forgetting. Was this like? Wait, was it 0? Wait a minute. No, it's not 0. Sorry. It's
Oh,
yeah, yeah, it has to
it
be an eigenvalue.
stabilizes.
Yeah.
Sure, sure.
Okay, so we see that in this case, this gives us, so if the original, so if you have like d qubits, then this gives us a 2d minus m dim Hilbert space.
Mm-hmm.
Because like this is like each of these conditions is like projecting onto the +1 eigenvalue, right? And they like all commute. So this like basically projects into one out of 2 to the m possibilities. So this gives us a 2 to the d minus m dimensional Hilbert space. So this becomes the code subspace, the cospace. Um,
Okay.
Okay, now we're going to get to homology part. Okay, so getting to the homology part, we're going to consider a torus. So we're going to discuss something called the toric code. We have a
Oh,
torus. Let me just cut it up and like draw it as so. And what we're going to do is we're going to cover up this torus with like these sorts of lattice lines. And we're going to define a bunch of stabilizers, but the first thing you need to know is that basically the number of vertices, there's Lx vertices in this direction, Ly vertices in this direction. So you basically have Lx, Ly qubits. So D is Lx, Ly at this point. And we're going to define some stabilizers. The stabilizers here are quite simple. So for every vertex, right? Yeah. Huh. Actually, a lot of this is up to convention. Let's see. In some cases, people place qubits on the edges. In some cases, people place qubits on the vertices. I like it when they place it on the vertice or the faces or whatever, but let me just check which convention I'm going to use. I think I will use the convention. I'm not sure if I have this for this. Yeah, let me check. Could you like pause the recording for a bit?
sure, sure.
Yeah.
Okay.
So as it turns out, you need to place a qubit on every edge, not every vertex. Huh, okay.
I see.
Yeah, this is interesting, but it's a bit underwhelming. It's not the deepest thing you've ever heard of. So for every edge, we have a qubit.
Mm.
And so for every vertex, we have a stabilizer. And the stabilizer is basically, if I recall correctly,
Would
we
it still
have
be LXLY qubits or would it be
two LX.
two two LX1? Okay, right. Sure.
Yeah. Yeah. It's the X operators for every vertex stabilizer. You have the stabilize. You have for every vertex, we have a stabilizer given by the product of the X operators on each of the vertices.
Yes, okay.
So like the X operator acting on like each qubit on like each edge, right? Like connected to that particular vertex.
Mm-hmm.
So like the product of
Yes.
four X operators. And
Why is it a stabilizer if it kind of does a rotation for every single qubit?
huh?
The poly X would do a rotation uh, of the qubit at each edge, right?
Yeah, I guess.
Uh, okay, wait. I'm understanding it. So, in general, if for general qubit state side for each edge, it will do a rotation. But
Yeah.
later on, we're gonna find the states where it is left unchanged. So,
Yeah.
um, okay, that makes a lot of sense. So essentially, we're looking for the states that are
Yeah.
positive in the x that has eigenvalues of +1 and -1 in the x direction. Okay, sure.
Yeah, we're looking for the states that have like, yeah, we're looking for the states that have eigenvalues of 1 for all the stabilizers. Those are the
Okay,
code states.
I
And
see.
for every phase, we also have a stabilizer. So a phase basically has like 4 edges and like um we now multiply all the z operators.
Mm,
Okay.
okay.
So that's that. Okay, cool. Um
So now we must look for simultaneous. I guess it's as simultaneously the eigen state for both of these stabilizers. Would that be correct?
Yeah, you'll have to
Okay.
be, it would have to be simultaneously an eigenstate for both of these. Right, yeah.
All right.
Um,
Sure.
okay. But I think like it would be, would it, okay, yeah. But let's change things up. What I just wrote here was the Wikipedia definition, but I think it's easier if you do Z for the vertex stabilizers and X for the phase stabilizers.
Sure.
Um,
Okay.
Z, 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 and X, 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 X. Okay, nice. So let me just like, okay, so we're going to like solve the equation. So we're basically solve the equation then like for like all stabilizers, psi is going to be psi. So this is like the condition that we're going to satisfy. Like, but like to get familiar with what we're going to do, we have to keep in mind that out of the 2 to the 2 Lx, Ly states, basis states, for like each, and we can write them in the in these basis states, we can write them as the eigen states of all the Z operators. So basically, if you have an edge, right, you have the qubit on one edge. The Z eigenvalue is either going to be 1 or -1. So if it's if it's 1 or -1, so if it's -1, we're going to draw this edge red. If it's 1, we're not going to draw anything.
Okay.
So a general eigenstate can be written as a curve, like blop, blop, blip, loop. So this is like a Z eigenstate, but like you can have weirder things going on. It could look like this. Like
Okay. The reason is because these are elements of the these are
no,
elements.
we haven't got to finding the elements of the stable. We haven't got to finding the stabilized states yet. We're just
Oh, okay.
writing
Sure.
out all the states of like the bigger Hilbert space, but using this graphical
Okay.
notation because this will make our lives easier.
I see. Okay. Sure.
We will now get there. We'll get there. Like it takes a while, but we're almost there.
Sure. Sure.
So
All right.
okay, so but we're now gonna apply the stabilizer conditions. Um, so the first thing that we need to note is that if we were to act vertex stabilizer on a state that looks like this is like just an eigenstate of all the Z operators. Let's see if we were to act a vertex stabilizer on this point. And just for fun, I'm gonna draw something like this. And this point. So at this point, we see that the surrounding points, qubits look like this. So they have Z eigenvalues of 1, 1, 1, and -1. So if we calculate the Z, 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 we see that we get -1, which is bad. Could you like lower the screen a bit?
Oh, yeah. Sorry.
No, it's okay. Like, because there's an odd number of -1 eigenvalues, you can see that the vertex stabilizer, this is a -1 eigenstate of the vertex stabilizer, not a 1 eigenstate. So it's bad.
Yeah.
Oops, sorry. Yeah, okay, my roommate just arrived, so yeah. Can you like pause the recording for just a second?
Sure. Sure.
Okay, so this is bad. Another example of what is bad if we look at this vertex over here, we see that there are 3 -1s and 1, 1. So Z, 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 Z in this case will be -1, which is bad. So we see that to be a stabilized state, you can't have either of these two types of vertices. So all the lines should basically form closed curves.
Right.
you can't have endpoints and you can't have points like this, so they should all be forming nice closed curves like so.
Yeah. Okay, cool.
And now we're going to look at the phase stabilizers. Recall that the phase stabilizers are basically
The poly X one.
yeah, x,
Yeah.
x, x, and x. If we try to apply this on this particular state, recall that what x does is basically flipping the z eigenvalue, right? So if we were
Yes.
to apply this to this curve, to this face over here, we see that basically the
Oh.
face originally looked like this, but now it gets flipped to this.
Yeah, that's cool.
So
Okay.
what you see is that basically applying all the applying all the phase stabilizers basically takes your original curve and then like
Deform the
adds,
curve.
yeah, deforms the curve in a way that's homologous to the original curve. But if you want to
Cool.
consider the quantum state that's basically invariant under all such possible deformations, you should add together all the curves that are homologous to each other. So we have
Right.
for the stabilized state, the sum of basically like all the curves that are homologous to nothing. So this is ket 0, 0. But there
See.
are other kets. Oh, plus like nothing plus blah blah blah. For example, you can have the ket 1, 0, which you can write as like the sum of all the curves that are homologous to the non-trivial homology curve going across the torus.
Cool. And then the 0, 1 would be the other direction.
Yeah,
And then 1, 1 would be I just realized then. But you could have curves that loop around twice, right? So does that
right.
mean you have a 2, 0 state,
But the
or you're only
interest,
concerned with
but the question here is that the z eigenvalues are basically like if you flip the z eigenvalue twice,
oh,
you just get nothing. So this
I
is
see.
basically like
Mod
Z2
2.
graded homology.
Right. I see. So the usual topologically speaking, the torus group, the torus homotopy group has is Z uh direct sum Z, right?
Yeah,
But then because of our interpretation of this in terms of uh the 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 eigen, we're only concerned with the eigenvalue. So if you go around twice, right, then
yeah,
the stabilizer would have an eigenvalue of +1. So essentially, that essentially does it essentially has an equivalence relation on the space of
yeah,
the homotopy. Okay, sure. So that in the end you end up with a Z2 graded.
yeah,
That's cool. Wow.
yeah.
Does
And
this
you,
generalize well to
yeah, it's
three
generalized.
dimensions?
Yeah, it is
I mean three
generalized
qubits. Cool.
because you don't need to have to be a square lattice. You can just use a triangular lattice and do this for any manifold. And by doing this, you will see that basically the quantum error correcting code would have a code subspace that is spanned by basically the Z2 graded homology of the space.
Oh, that's cool. So if you have a manifold that has essentially the homology group has is three-dimensional,
Yeah,
then you can encode 3 qubits.
yeah.
Um, and I suppose, do you have an example for a manifold that is has a homology group of three like independent directions?
Wait, let me see. Would this one work? Um, let's see if this one works. If it no, wait, that's too many holes. Let's see if this one works because like I think it might. Not entirely sure though, but like I feel like it might. So this one exists. This one also exists.
Mm. Then there's one
Um,
that goes between
is this
them.
4? No, the one that goes between them.
Uh,
This is homologous to nothing.
as in the one that goes from one hole to the other. So if I draw it in
This one,
orange, yeah,
but this one is the sum of these two.
right. Um,
But wait, let me see more. So we have
maybe we need
this,
one more Jiwoo. Oh, right. We have that.
but we also have this. So now we have four. Like I think we have four now.
Oh,
We got
oh well,
stumped.
we can always use four and then just can we just ignore one of the qubits? Would that
Oh,
work?
but oh yeah, we could, but like the thing is, like in principle, nobody uses the toric code because it's hard to place qubits on like a torus, right? You don't have a torus in real life.
Right.
So this has nothing to do with real world applications.
Oh, oh wait. But then it is hard to place qubits on a torus, right? But there is a my mentor did something with regard to topoelectrical circuits where he essentially placed quantum states, essentially placed quantum states on any because um if you're doing condensed matter system, you will need to build a torus, literally a torus, right? For
Yeah.
the lattice, which is hard. But if you are building circuits, you can put the wires. The wires can go from any point to any point. That would be seen
Yeah.
as the edge. So
That's cool.
uh yeah, and then he did it for the SSH model, right? This SSH model. And then he
Yeah.
did I have understood the SSH model quite well. But then he did it, he went on to do it for things like the whale semi-metal and the uh what else? Yeah, he did mention that the good thing about this is that you can literally take points from any point in the circuit to any other point, and then that way you can realize higher dimensional um
Huh.
higher dimension. I
Yeah.
wonder if he has considered toric codes. Oh, that's really cool.
Yeah. Like this was the coolest thing in the class for me so far. And then they like went on to like building quantum computers. And I was sad because they didn't do
Mm.
topology anymore. But like yeah. Um. Yeah. I like to learn type theory now.
Cool. Okay. Oh, yeah. Okay. Actually, maybe I'll ask my mentor if he has ever thought of this because I did wonder like why would you want to build? I mean it's cool to build quantum states on very exotic manifolds, but like is there any reason for doing so? And you have just given me a reason for doing so, right?
Yeah. But like the Google quantum computer, they just use a surface. So like
Yeah.
so they just do homology for manifolds with boundary, and they just do this, which can be very boring. Um,
Yeah. Cool. Okay, sure. So now we can transition to talking about oh, you left the room? Oh,
oh no,
uh
I'm joined again.
sure. So let's talk about type theory. Okay, you're a bit familiar with Java programming, right?
Yeah, a little
Okay,
bit.
actually this requires less of math and more of a bit of coding, but
Yeah.
sure. So okay, so the study of types, right? In types in programming is there's integer types, right? There's string
Ah,
types,
yeah,
and then there is floats, right, which can represent decimals and stuff.
yeah,
Uh, the study of type theory brings this to the extreme, and the main goal, the main thing, the main punchline is that mathematical claims, right? Mathematical claims are types as well. So you have a type of 2 plus 2 equals to 4, you have a type of 2 plus 2 equals to 5, right? Clearly 2 plus 4 equals to 4 is true, and 2 plus 2 is
yeah.
5 is false, but both of them are types. So for every mathematical claim, you have a type,
Wait,
okay?
so every
Uh,
mathematical claim is its own type,
yes, Riemann hypothesis, the knot of Riemann hypothesis, stuff like that. Every single
but
a
there are
lot of
way too
epsilon
many
law.
types. Though.
Yes, so in fact there are way too many types. Um, but that's okay because the we can okay, so there's so many types. So clearly the computer cannot store all of them. Um, so the type is okay. So but most of them are actually not. So what distinguishes between a type of 2 plus 2 is 4 and 2 plus 2 is 5? The difference is that there's a proof for 2 plus 2 is 4 and there's no proof
Yeah,
for 2 plus 2 is 5, right? So how do we distinguish the two? It turns out that when you have variables, right? With variables,
yeah,
um, when you have variables, you can have an integer variable that's let's say 5, you can have an integer variable that's 4, you have a string variable that says hi or hello, and float you can have like 3.14.
Yeah.
So it turns out that variables of a mathematical claim type is a proof is a
Oh,
proof for that for
but
that
you
type.
can have inequivalent proofs.
Yes, exactly. So uh that's a huge tension right now we have. So okay, so if our 2 plus 2 is 5, well, then we have no proof for that. So there's no variables of that type. Like any mathematical claim, right? If there's a term, right? Sometimes we call it
Yeah.
a term of a type. If it's or sometimes we say that if the type is inhabited, these are just different languages
Yeah.
for the same meaning, or if it is a variable of that type, then that variable is a proof, right? That the term is a proof for that claim. So Riemann
Okay.
hypothesis, I don't want to make any bold claims. So okay, so yes, you just mentioned something very important, which that there could be multiple proofs for a single type.
Yeah.
Okay, before I get to that, I'll come to that later. But first, let's examine what we can do. Okay, so this correspondence, right, where essentially types are claims
Yeah.
and and terms, right, inhabited types are proofs. This entire thing is called the Curry-Howard correspondence. You can search the Curry-Howard isomorphism of correspondence.
Yeah.
Yeah, Curry-Howard. And okay, so what would now okay in programming you can form a pair type, right? A pair would be a pair of maybe let's say integers or and strings, or it
Yeah.
could be a pair of integers and floats, or it could be any other pair of two types. So if you want to form a pair, if you want an element, if you want a pair of this type, you need to provide uh p must be an element of q and
Right.
sorry, p must be an element of integer and q must be a um element of string, right?
Yeah.
Essentially,
Oh,
you
so you
if you
need
want to
two claims and two proofs for each.
exactly. Exactly. So this pair types, it turns out that in Curry-Howard correspondence, right, it
Yeah.
corresponds to the logical n, right? Does that make sense?
Yeah.
If you want to prove 2 plus 2 is 4 and uh 2 plus 3 is 5, you need a proof for each one of this and this, then you can form a you can form a you
Oh,
can
that
form
makes
a
sense.
pair,
Yeah. Huh.
right? That makes
That's
sense.
interesting. Okay.
So then you can have this product type. So pairs are kind of product types. You have A and B. A pair A B is a term of type A cross B, A times B.
Yeah.
Um,
Okay. Then what
so this
about
will later
or?
gen. Great. So what about OR? It turns out okay. This is a bit nuanced, but if you think of the type as this blank space, right? A
Yeah.
and B. Um, okay. So what does it mean uh to okay, so A or B, right? A or B is true if either there's an element A, right?
Yeah.
That could be one case, or you can have another case where it's a B like this.
Yeah.
Or you can have both of them, right?
Yeah.
Um Essentially A or B is essentially the the sum of the two, the sum
Right.
of the two space. So essentially A plus B, you can think of it as a direct sum.
Yeah. Yeah.
Essentially this is the OR type. Is logical OR. However, there's a small nuance which is that um let me see. There's a small nuance which is that you you it's actually a truncate there's actually a truncation involved because essentially we if we include law of excluded middle, right, which says that
Yeah.
every claim every type is either inhabited uh
Or
or
not.
not, then then if law of excluded middle is a term of this type, of this sum
Yeah.
type, this sum type. However, right, we do not know which one it actually lies in. I mean, if we could extract which one it lies in from the law of absolute middle, then we have essentially solved Riemann hypothesis and every other great thing, right?
Yeah.
Um, so we do not actually know which one it comes from. So we actually say that is a element of this type, but it's truncated at level level one basically. I'll get to the level one and stuff is a bit more involved, but essentially this is saying we when we truncate, right, it's essentially
Yeah.
saying we forgot which one it came from. So logical or and the sum type is actually, to be very precise, is actually truncation at H at a homotopy level of one.
Wait,
But
what
but
does this truncation mean again? Like, I'm confused because
the truncation, um it essentially, okay, I can't really explain much about the truncation. I just want to, because I'm not, it gets a bit more involved. But for all purposes, I'm just bringing the truncation because I want to make this claim more precise. Like it's just a nuance. It's actually, to be
so
very
like
precise,
so
it's actually
so
a truncation.
the data type for A plus B is basically,
Mhm.
if you want to store a
Logical or,
variable, that variable is a proof of either A or B, but we don't know which one.
yeah. Essentially, the reason why I'm introducing the truncation, because we don't know which one it is. But for all purposes, you can just think of it as A plus
So
B.
the variable just like is a proof and it's either A or B, but the variable itself just doesn't contain information about which one it is proving.
Yes.
Okay.
Yeah, that's right. Okay, so we have done logical and, logical or, logical not, right? Logical not.
Yeah.
What is logical not? Um, so this is where we need to introduce a notion of an empty type. So I'm gonna define a type empty, and
Yeah.
essentially this empty type must not have any. It does not have any terms of the type. There's no variables that inhabit it. There's no
Yeah.
terms that inhabit it. So actually, a not of A, logically, not of A, it corresponds to. Okay, actually, I need to talk about functions first. Okay, sorry, I'll postpone this to slightly later. Let me talk about functions. So if I have a function from, bringing back to programming, right? If a function from, it takes in an input, or we can think of a mathematical function. If it maps from A to B, right? What does this correspond to in logic? So you can think of it as, perhaps I can, if I have a function of the type that brings me from type 2 plus, or rather, x plus x equals to y, and it
Yeah.
brings me from to x equals to y divided by 2, right?
Yeah.
Um, if Basically what I'm trying to say is that if you give me a proof for why x plus x is y, the fun
Yeah.
and you give me a function f, right, that can bring me from x plus x is to y to x equals to y over 2,
Oh,
then I
okay. Oh,
can
yeah.
I can turn your proof p, I can
Yeah.
turn your proof p into a proof f of p for
Yeah.
this other statement. So actually functions are just logical implications.
Yeah.
Okay, so that's great. Yeah, so the whole structure is going to be built on functions. The whole type theory is going to build on the notion of functions, because that carries logical implications.
Yeah.
So back to not, right? How do we define not? How do we define not of A? The answer is that it's actually a function from, uh okay, I'll just call this not. It's actually a function from my A to the empty type. So essentially this is saying that if you can if you can if you can provide, um okay, so if,
Yeah. Okay.
yeah,
Yeah, that makes sense. Yeah.
so so a term,
But you're saying that the function mapping nothing to nothing is a function, right?
um function mapping from nothing to nothing is a useless function, because, yeah, it's a useless function. But in general, if you have a type A right over here, an
Yeah.
element of the function type from A to empty, it is a
Yeah.
proof of not A, because now if you can provide me an A, I can give you an element of empty, but we know there's no element of empty.
Yeah.
So that must imply that you cannot provide an element of A. Yeah. So a proof of not A is essentially a map from the function. It is essentially a term of the function type from A to the empty type. Yeah.
Yeah,
So we have covered.
but if a function from A to empty exists, then the function should map nothing to nothing.
Um, it should map nothing to nothing, but this function eats. Uh, okay, so yeah, right. So you're right to say that it maps nothing to nothing, and that
Yeah,
implies that A is nothing essentially,
yeah,
right? Because yeah, you're right to say that. That's one interpretation. A is nothing because if I can give you something,
yeah,
then yeah, okay, you're right. Okay, so we've covered mathematical claims, right? Proofs are terms that inhabit that type, and there's a
yeah,
logical and logical or functions, right? Which are logical implications and not. So this allows us to do first order logic, right? Because we can essentially make all the claims. We can make claims, and then we can have or, we can have and, and then we can have these are just logical symbols for and then or. Then we
yeah,
can not have a. And then we can have A implies B,
yeah.
and that's first order logic. But that's not enough because in math we deal with second order logic, right? And what a second order logic is basically involving the
All,
symbols for all x some f of x, right?
yeah,
Of that exists x such that f of x. So how do we encode this in the in the in the in the type theory? So this is so this is where dependent type theory comes in. So if you search anything related to type theory, you'll see the word dependent type theory. So what is
yeah,
dependent type theory? Um, roughly speaking, is this is where a bit of the language of uh, fibers comes in. Um, and at best, I feel like it's just an analogy to uh, the topological notions.
yeah,
But essentially, it's quite simple because for proof of x, for proof, okay, so I'll just give you the punchline. This turns out to be the product type, and the product type is essentially you can think of it as if for all x, right? Let's say x in
yeah,
the natural numbers, f of x, right? Then essentially it's a product type of f of 0
yeah.
times f of 1 times f of 2 and so on.
Wait, but it's
And
infinite. You
if
can do that?
yes, you can do that. So yeah, you can do that because this is actually the okay, you can think of it as big. Okay, I'll just talk about the other part before I talk about dependent functions and how you
Yeah.
can define this rigorously. But essentially, exist is a sum type. So product type we always denote it. We can denote this as product of x
Yeah,
in
I can see that it's a sum. Yeah. But but
and
but
this is the
I'm
sum.
not convinced that like
You can define that.
you can have infinite products because computers have like
Sure.
infinite don't have infinite memory.
Yeah, you'll be right to say that. So okay, so this is the sum of f of 0 plus f of 1, and strictly speaking, it's a logical truncation at the first homotopy level, but
Yeah.
that's just a nuance. So how do we define such things? It's actually okay, so if you want to define it for all natural numbers, right, that's a problem because there's infinitely many products. So
Yeah.
actually, uh, you can actually still you can still do it. Um, you can still do it, and the answer lies in how we define natural numbers. So
Yeah.
to answer your question directly, this is where uh, the natural numbers is actually defined inductively.
Yeah.
The natural numbers is actually inductively defined, meaning
Right.
that if you want to and how it's defined is defined as the natural numbers. You can form a term of the natural numbers using via two ways. One is the zero, right, which is a term of the natural numbers,
Yeah.
and another way is the of successor of a natural number x,
Yeah.
where x is where x is a natural number itself.
Yeah.
So um so essentially, if you want to define a function on natural numbers, you need to define it inductively, meaning that you need to define how it acts on f, the function f. If it brings natural numbers to let's just say another natural number, I need to define how it acts on the zero, right?
Yeah.
And I need to define how it acts on n plus one in terms of some formula on how it acts on f of n, and then this one n.
Uh-huh.
So So example, if I want to define the f of x equal to 2x, right? How it look like is f of 0 equals to 0 and f of n plus 1 is equals to f of n plus 2.
Yeah.
Yeah.
But
And it's
how do you
actually
do
all,
like all real numbers?
oh, for all real numbers. So if you want to define real numbers, you need to first define the the rational numbers. And the
Yeah.
rational numbers will be essentially so if you want to define a function from rational numbers to some other type, you need to define, I'll just call this Q, I'll just call this G. You
Yeah.
need to define how it acts on the pairs, right? Of P over P and Q.
Yeah.
So the rational numbers is actually a is actually is actually natural number, like it's actually a pair type.
Yeah.
Um, but then you're making some identification. I haven't really defined the natural numbers before, but essentially you need to do this quotient sum equivalence relation. So you need to define how it acts on PQ for for every pair P and Q.
Yeah.
And yeah, that's how you define it. And then if you want to define the real numbers, so you can define real numbers as there's a Dedekind cut, right? The
Yeah.
Dedekind cut construction of the rational numbers, which is the Cauchy sequences. And then you find the value that converges to. So you need to find the topology and every other thing. And yeah, so that would be the way to define a function on the real numbers. You need to go through this map, this
Yeah.
entire route. But that's pretty much any construction that you can see in a standard analysis textbook. So it just corresponds to how do you define an analysis in type theory. And I think that's quite well done already. Yeah.
Hmm.
Okay. So essentially, product types. You can think of it as product types. I claim that product types are sections. Types are sections. Uh, and some types um is just an element of the total space. So what this means is that if we think of the base, right,
Yeah.
as a type A, or rather in this case, let's say n.
Yeah.
Let's say let the base manifold be n. Uh, Okay, I'm using manifold very loosely here, but then essentially, if this is the point 0 and this is the point 1, this is the point 2,
So
then
going up is like a different type of F.
these are fibers on the base manifold. So this fiber will be um f of 0. Okay, this okay, let's say I'll just make it a bit more concrete. So let's say f of x is the claim. That's the
Yeah.
claim that x plus x is 2x. So this will be 0 plus 0 is equal to 0. This will be 1 plus 1 equal to 1. These are all types. And this will be 2 plus 2 equal to 4. These are all so you can think of all the claims over here as a fiber over the thing that we are iterating over.
Wait. The claims are the fibers. I thought the claims are a point on the fibers.
Uh uh the claims are
Because if it's a section, then if a section of a fiber bundle, it passes through a point on each fiber.
oh
But
okay. Product types are okay. Sorry if I was a bit loose with the notation. Product types are are are, are the okay, maybe a term of the product type is a section.
yeah,
So the product type itself of x in n, where x plus x is 2x. This this object over here, this type over here, this product type is
yeah.
the entire space, is the entire fibered space, where over
Okay, yeah,
each over each point on the base manifold, over each point on the for every value of x, right? You
yeah,
have a claim attached to that point. And this
yeah.
claim is a space in itself because it can have maybe one proof, it can have two proofs, and so on.
Okay,
Oh, okay, actually, uh, okay, let's just say it's one proof. So as long as I can provide one proof of it, it'll be enough to, yeah. So there might be two
okay.
proofs,
That
but
makes sense. Yeah.
yeah.
What is the sum type?
Uh, okay, so the sum type is actually just, so a term of the sum type is just a point, right? A point
Yeah.
in the total space E. So you can think of the same fiber thing, just
Yeah.
that, so this is N, just that I only need one guy in any one of the fibers. I just need one guy. So I
Yeah.
just need one at one point in the total space. So essentially a term of the product type, right? A proof that for all something something, that claim
Yeah.
of X, right, is a section because I need to provide many points, many terms,
Yeah.
and each fiber needs to have one term. Whereas a proof of the sum type is just one of them, because then this will be the guy that yeah. And strictly speaking again, whenever we deal with OR, the logical OR, right? Because these are
Yeah.
the sum type is actually a bunch of ORs, so we need to have truncation, but that's not too important for the context we're talking about now.
Oh, so the truncation is like you can move the point sideways and it's fine.
Yeah, so the truncation basically, so the issue right now is that if I give you a proof of this sum type, right, you
Yeah.
can, if I don't truncate it away, you can project it down and you can tell me, oh, exactly which guy is there,
Yeah.
exactly which number that does this hold true for. But the truncation, you can think of it as if I truncate it away, then I'm just saying, oh, I have a I have a term of this sum type, right? So this is okay. So this is the
Yeah.
non-truncated version, and the truncated version, you can think of it as I'm forgetting all the fibers, right? I don't know where I have this guy, but I don't know it comes from here or it comes from here or it comes from here. So essentially, that's the idea of truncation.
Yeah.
Roughly, strictly speaking, truncation is actually uh uh okay, yeah, I'm not too sure, so I don't want to say anything wrong. So essentially, this allows us to do second order logic, right? In terms of and the reason why it's dependent type theory is because these are known as dependent functions, right? So that this product type and this sum type, they are dependent functions. And
Yeah.
why is it dependent functions? It's because previously I said f of a maps to b. You can think of that as a fiber of b's over a's, right?
Right.
And every element of a gets mapped to some guy of b, and all of these fibers b, they are identical, they are the same fibers. However, right, if I have the if this one b is basically a constant fiber,
Yeah.
but if I have 2 plus 2 is 0 plus 0 is 2, and 1 plus 1 is 2, 2 plus 2 is 4, these are different fibers. They're different types. So essentially
Right.
this is a constant type function where the codomain, right, is a constant type. Yeah, codomain is constant, but a dependent function, right, it generalizes the notion of this function, and that's where f of a is a b of x, where your codomain actually depends on the type of the type of it actually depends on the input to the function.
Right.
This sounds
Yeah.
really cursed. It kind of looks cursed because essentially this kind of essentially saying that I can have a function in math, right, that takes in zero and
Yeah.
gives me a string high, right? And then or rather, okay, let's not say it's a string. Let's say it's an element of a group. Uh, or let's say it's an element of group G of SU2, and then
Yeah.
I have f of one, right? And then that gives me an element of another group. Let's say SO3, right? And that's really cursed because yeah, we're not familiar with these type of functions in math. But it turns out
Yeah.
that this is the exact type of notion we need to deal with when talking about encoding second order logic and type theory. Yeah. So this is starting to make us feel a little bit uncomfortable, but it's still kind of acceptable because it doesn't it's just we're just unfamiliar with it. Yeah. And okay, so here comes the fun. Here is where we just start to see problems. So it seems like all is great, right? But there's actually a lot of problems in type theory. So for example, um, let's define so associativity, right? Associativity of a group is basically a term of the type A, B, C maps maps to uh A, B, C essentially, right?
Yeah.
But the problem is you see if I have the associativity in two ways, A, B, C, D. right? And how do I
Yeah.
prove that it's equals to? So this is something that we want to put in our. This is something that we want to put in our. This is something we want to claim. We only want to do
Yeah.
it once, right? We don't want to do it for every single higher associativity, because then there's infinitely many that we need to define.
Yeah.
And that's we just our goal is that from this alone, right? Hopefully we can do it for all pairs, like for example like
Yeah.
this. But the issue lies in that okay, so this is actually there's actually two ways to go about this. One is to do let me try to get this right. So one is to do A, B, C, and then D, and then after that you do A, B, C, D,
Mm.
and then after that you do, yeah. So this is one way, but another way would be to do A, B, uh, C, D,
Mm-hmm.
and then from there you do uh, A, uh, A, B, C, D. Just let me
Just
let
go
me think
immediate.
about it. Oh. So you just do A, B, C, D. Um. Yeah, and then you're done. Yeah.
Yeah.
Oh, so actually this directly goes there. Okay. So you see that this is actually known as a pentagon. You see some of this. If you come across this pentagon structure. Uh. Uh. If you do things like monoids and things in computer science. I think there's some claims that this is actually the same. There's some people that I think if you add an axiom that this is commutative, right? Then but then it's all settled. But essentially the problem you see that is that there's two proofs. There's two proofs of associativity. Uh, there's two proofs of associativity. Sorry. To be more precise, there's two proofs of A, B, C, D. Mapping from this thing to A, B, C, D from
All
this
right.
this thing, right? So there's two proofs. I'll just call it A1 and A2. And both these are both elements of this type. I'll just call it A. These are both terms of this type. So now is an issue because uh previously we said that propositions, right? They are propositions, mathematical claims, they are types. And just now you said that there could be two proofs of the same claim.
Yeah.
Uh, but it turns out we don't really want two proofs of the same claim because uh, because if you can provide two proofs of the same claim, we want to we want to we want to construct functions out of that claim. So if we actually want to make a statement that two proofs of the same claim, they are essentially the same because if we can provide two proofs of the same claim, right? Imagine now that I want to have a function that goes from A to B.
Mm.
Then, if I want to define a function from A to B, I'll need to define how it acts on A1, right? And then,
Yeah.
so this is something that I need to provide to the computer. I need to write out of A2, and this is an issue because if they, if we build higher proofs, right? We could have many proofs. Um, yeah, we could have many proofs of 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 the same claim, the same
Mm.
proposition, and that's an issue because now if I want to use that proposition, right, to form a logical implication to some other thing, then I need to manually provide how this function acts on each of the individual proofs, and this is known as proof relevance. So essentially, proof relevance is bad because if I have proof relevance, right, and I'll construct and I'll use this proof of some statement
Yeah.
to
Yeah.
form another statement, right, then I need to do it many. It gets worse and worse. Yeah.
Right.
So essentially, we want to say essentially that all proofs of propositions, right?
Yeah.
Propositions are the same, are identified, are equivalent. Equivalent is a key, right? Because we need a notion of equality essentially. We need to form an equivalence relation, um, and that's what's going to lead us to homotopy type theory. Okay, so the reason why we only want this for propositions because clearly, right, the natural numbers is type as well. But clearly
Yeah.
zero is not the same as one, it's not the same as two. So we want some types, to still have the set structure, right? And we want some types to still have we want some types to have the set structure, and we want some types to be able to have only one, at most one element.
Hmm.
Yeah. So essentially that's the identification we want, right? Propositions, we want to say that they at most have one term, whereas sets we want them to be as free to have many terms as possible. Yeah. And this leads to the natural notion of homotopy um because yeah, we want the notion of equality. So that brings us to the essentially the third chapter of equivalence and equality. So previously when I wrote 2 plus 2 equals to 4, right, I actually glossed over this part where what does it mean for this is a term, right, of a natural number,
Yeah.
and this is a term of a natural number. Um, how do you know that they're equal? Uh, yeah, so the notion of equality is actually encoded in paths. Okay, let's not say that so early. But what if we look at equality, we want 3 properties. We want reflexivity,
Hmm.
we want uh, uh, symmetry, and we want transitivity.
Right.
And this is actually very, very, very similar, right? So this is equality, but this is actually very similar to the notion of paths. So if we think about it as terms of path, reflexivity kind of corresponds to a constant path, right?
Right.
Which just sits there. The symmetry kind of corresponds to the inverse path, and transitivity kind of corresponds to composition of paths. So
Right.
in type theory, equality is essentially paths between terms. So if I have a space A and I have 2 terms A1 and A2, right? If there's actually a type, right? Of there's actually a type. It's a dependent type, right? Because it depends on what A is. Um, this is actually a term. Sorry, this is actually a type. So yeah, so the equality is actually is because it's a claim, right? And
Yeah.
claims are types as well. So this is actually a type. So if I want to prove, so I need a proof, right, of the equality of 2 elements of a type is a term of that type.
Yeah.
So essentially maybe I have a proof that A1 equals to A2, right? This is a V1 proof. But then we run into the almost the same issue because now we can have another proof of the same of the equality. Like yeah, so we want to okay, so this is where so if this is a type itself, we kind of run into a very circular argument where if P and Q are 2 terms of this type, then is P and Q, we can ask is P and Q, there is another term, right,
Yeah.
of A1 equals A2, right? This is a type is itself, right? So yeah, so by wanting to define the equality type, right, we wanted this, but by just wanting this, right, so we wanted to say that if A is a type, then that leads to uh an equality type,
Yeah.
right? But then that open a can of worms, right? Can of
Right.
worms because by wanting to define, say that if A is a type, then there's an equality defined on a type, which is a type itself because it's a claim, right? But if that is a type in itself, then there's an equality on the equality on the equality on the equality, and this turns out this is analogous. This is pretty much the same as the infinity groupoid structure in category theory. So I don't know much category theory, but uh in category theory, I do know that there's objects, right? Objects, and then there's morphisms between the objects.
Oh yeah, yeah, yeah. And then you have morphisms between the morphisms, and it goes again and again.
Yeah, so you have morphism between morphisms. So then you have yeah, the morphism between morphisms and so on, and then you have functors, and then if I have 2 of them, then I can have this thing, and essentially and then if I have even more of them, right, then essentially if there's another one, then there's this one. So essentially it's arrows between arrows between arrows between arrows, and that's essentially that's just pretty much what we mentioned so far, because uh um because equality. So that's where we say that's why we say that equality is a path, right? And that's where homotopy comes in because in paths, right? So equality, equality of equality of equality of equality, proofs of equality recursing on themselves, that actually corresponds to homotopy. Because homotopy is just path between path between path between path.
Oh yeah.
So that's where the interpretation of homotopy comes in. Because if you have a path between A and B, sorry, A1 and A2, right? Then
Yeah.
there's a path between the path, and then there's a path between the path, and that is a homotopy essentially. Um, yeah. So actually, so it seems like this is a issue because yeah. So this is the whole okay. So why does homotopy come in? That it actually comes in homotopy groups actually come in this sense because the identity, the reflexivity, right, is a
Right.
constant type, and that's essentially the identity on A, and that identity on A, right, everything is equal to itself. So this identity always exists. And it basically says that A is equals to A for all A. Um uh yeah, maybe I can put it for all A over here. So it will be a product type. Uh yeah, identity is essentially a product type. But then, so that's one proof of A equals to A itself. But then I could, if I have another proof of it, then that will actually lead to the homotopy. So if I have a proof of A equals to A, if A equals to A, right, identity map will just be the constant path, right? But if I have another proof P
Hmm.
of A equals to A, then that is a path from itself to itself. And then and by transitive property, I can have P at P of P essentially, and then that will go 2 rounds and 3 rounds, and essentially that leads to homotopy structure. So that's also a reason why we you can see the parallel between homotopy and
Yeah.
equality, um, and that's why we call it homotopy type theory. Uh, so we went from so I think that's pretty much all. Okay, so
How is
okay,
this
maybe I'll just
useful?
talk about. So why is this useful? Oh, it's useful because this is an alternative foundation, a
Yeah.
proposal for an alternative foundation for math, and that's because computers like types, right? Computers work well with types, but computers do not work well with sets because in order to define natural numbers, you need to define. It really takes infinite memory. So um, uh, I think formalizing math in set theory in computers, in the language of set theory, is difficult because of the infinities that appear.
Hmm.
But defining types in computers is okay because essentially there's infinitely many of these types that exist out there, but
Hmm.
we only we are only caring about the ones we can reach from existing types. So the whole is kind of a construction of sorts. In the computer, if you want to define math in the computer, most of what we're doing in proof assistance, right? Proof
Hmm.
assistance is we are constructing types. So essentially, proof assistance is all about constructing proofs, right? Constructing proofs, and essentially by constructing proofs, we are constructing types, and that is something that we can tell the computer to check very manually. And proof assistance is quite important in math because nobody understands fully the entire proof of classification of finite groups, right?
Yeah.
Classification of finite groups because it's 10,000 pages long, and there could be mistakes because I mean even experts, their intuition could fail sometimes. So essentially, the only way that we can be really sure that our entire tower of math doesn't crumble, um, because as we're going to higher math, it gets more and more intuition based, where you kind of feel that something is correct, kind of feel that something is wrong, and that's
Yeah.
shaky for math because if you go too high, right, and then you realize one of your intuition is wrong, then the tower above kind of just crumbles. That isn't good. And the issue is that we might spend a lot of time wasting studying the higher structures and then realize that something is off. So we want proof assistance. I do believe that the future of math kind of lies in proof assistance because that allows us to build a structure that the computer can verify, that is
Yeah.
correct. Like you cannot fool the type checker essentially.
Well, that's
And
nice.
yeah, so the reason why I'm studying all this is because I do believe in proof persistence, and in
Mm,
order to better understand proof persistence, I think it helps to understand type theory. Um, and okay, so lastly, equivalence. This is something I'm not super sure about, but equivalence is a notion of if I have two functions that map from A to B, and if I have two functions, okay, let's just say it's natural numbers, natural number to natural number, and it maps, let's say, two to, let's say it maps x to, uh, okay, okay, basically, this is something to do with function external extensionality, extensionality, because basically we want to say that if f of x equals to g of x for all x, right, in the codomain A, so f and g are functions from A to B, then we want to say that if f of x is equals to g of x for all elements in x, then f equals to g as functions. Uh,
right.
so, so this is equality is a type, right? So this equality is a type from of and where it's based on is based on the function type. So essentially this is kind of saying this kind of lifting. So we have our space B. Okay, we have our space A. This is essentially a homotopy lifting because for every point in space A we have a B, and we are
Yeah.
saying that if two functions have the exact same thing, then we are we are saying that they are equal. Yeah, this is kind of lifting. There's a lot of things to do with lifting that I'm not super sure about, but this kind of lifting from the space from the space of B, right?
Yeah.
From the space of B, lifting the definition to equal. So essentially, it's equality on B, right? It kind of lifts to equality on A to B. Yeah, it's function extensionally essentially lifts a notion of equality on B to a notion of equality from all functions to B. And uh and this is essentially saying something like F is equivalent to G. Um yeah, so equivalence is another similar notion of equality. Um Equivalence is a similar notion of equality, but it's defined differently, right? It's defined in
Mm,
terms of something like this. Um Yeah, so equality is quite strict in some sense because you're saying literally that two things are equal, but
yeah.
equivalence is kind of is a bit nuanced what you might mean by this. Yeah, but it's I'm not okay. Sorry if that wasn't very clear, but the takeaway is just that equivalence is similar to equality, but it's not exactly the same thing.
Yeah.
However, right, there's something that is basically the holy grail of type theory right now, which is univalence
Yeah.
axiom. And essentially, univalence axiom says that equivalence, right, which is denoted with curly equals,
Yeah.
A is equivalent to B, right? And how does it relate to A is equals to B? Univalence says that these two notions get equivalent. So this is where you see terms like cubical type theory and univalent foundations of math. These are all similar vocabulary that you see floating around this univalence axiom. And you can define it this way. You can so to define the univalence axiom, you just say that this univalence axiom is literally a term of this type.
Yeah.
And so this is the axiom that we include. So whenever we throw in axioms, we basically just say there is a term. Um, and the main challenges in today, this is still an open question. I think the main open question is, can we find a model in which univalent type theory or cubical type theory holds? So all that we mentioned so far, logical foundations and stuff,
Yeah.
um, path homotopy type theory, I do think that I'm not super sure about the details, but there is a model in a Quillian categories apparently, but I don't know enough category theory to say.
What do you mean by
But
a model? Like,
oh, okay, I don't know a lot of model theory, but a model is basically we can define all these logical we can define all these logical foundations, but model is basically a realization of that foundation. You can kind of think of it as a representation of a group.
Okay. Yeah.
So maybe if I give you a concrete example, there is a model in which ZFC holds, and then there's another maybe model X in which ZFC hold, and then another model Y in which ZFC is excluded, it does not hold. Sorry, ZFC, sorry, not ZFC, choice. So
Mm,
notion of action of choice is a bit contentious, right? There's different models in which whether choice hold or whether choice does not hold.
mm,
So likewise, there's a model where univalence axiom, where univalence axiom holds, and it's basically a choice whether we want to put that in the theory or not. So uh, maybe there's a model in which univalence hold does not hold, and then the math that we can do with that model is quite limited.
mm,
So we are looking for a model where univalence holds because the math can do that with that is more freedom. This is model theory is not something that I know super well, but essentially we want to find a realization, a concrete realization. This is kind of like the abstract group structure, and we want to find a realization that actually exhibits exhibits the univalence axiom. So this is an axiom, but yeah, in order to do real math with it, we want to find a model in which it's true, then we can construct math on that model, and we can do fun stuff. Yeah.
mm,
So maybe if I were to summarize what I've just said so far, um, essentially, type theory, right? We generalize the notion of types in programming languages to say that claims or propositions are types. Then logical and is just a pair, logical or is just a sum with some truncation as a nuance. And then functions from types to types are just logical implications. Not is a function from the type to an empty type, right? And then that allows us to do first order logic. Then second order logic will be it involves fibers, dependent functions because the fibers are not constant. And essentially it tells us that product types and sum types they are logical for all and for that exist. Um, if you want to define functions that act on infinitely many if you actually want to define a function that acts on infinite many things, you do it inductively. So for example, on the real numbers, you do it this way.
mm,
Uh, and then okay, so then of course all this notion, right? It seems like we are all great because we can do first order logic and second order logic, and that seems like we can do all of math. But we realize that there's a lot of issues with regard to equality, right? We have two proofs of the same statement. That leads to issues if we want to construct, if we want to continue doing logic with it, because we run into more and more, the functions need to be defined an increasingly greater number of terms of that type. So we want to kind of collapse down the we kind of want to say that all the terms of the type that motivates us to define equality because we essentially want to say they're equal. So
mm,
you just need to define a function of one of them, and then the rest of them are equal. So we want to define equality so that there's this equivalence relation kind of notion. Equality then led to the notion that equality is a type. And then we saw that opened a can of worms because if equality is a type, uh, then you have infinity groupoid structures, and that leads to homotopy. Um, and in order to and yeah, so that led to a lot of structure. Uh, and actually we solved all this structure using truncations. So essentially truncations are saying that the how many the nth homotopy group
mm,
the nth homotopy group is trivial because essentially if you truncate uh if you truncate the type right at a certain level, right, that's what truncation level roughly means. If you truncate at a certain level, then you're saying that there's no morphisms between morphisms, there's only morphisms between morphisms. So I'm kind of saying that oh maybe it dies at this level, right? This guy is a unique morphism between morphisms, and that's what truncation roughly leads to. So like the first truncation level, I'm going a bit further, is essentially contractibility of like in a similar notion from topology. The second level is actually propositions. Essentially this is saying that there's at most one proof.
mm,
Then the third level is actually essentially So this is level 0, this is level 1, level 2. Sorry, the second level is actually a set, a notion of a set. So a set has how many fixed, finite, not finite, discrete terms of that type. And then the third level is essentially groupoids, because uh, you have morphisms between the objects in the set, kind of.
Mm,
Um, so these are all types. These are all 0 type, 1 type, 2 type, 3 type. They're all truncated at different levels. And roughly speaking, that just means that uh, where you stop drawing the arrows between arrows. Yeah.
mm.
Yeah, this is not super rigorous because I find that it's a balance between rigor and a lot of lectures I see online, they talk a lot about rigor, but then it feels quite unmotivated. So I've constructed this narrative to motivate type theory a bit more and why it leads to all these issues and topics. Yeah. Then lastly, equality is cool, but we want equivalence, right?
Yeah.
Because functions can be equal. And then the univalence axiom says that equality is equivalent to equivalence. And now the main thing that people are trying to do is trying to find a model in which this univalence axiom holds. And apparently, if they can do that, then we have successfully formulated mathematical logic in the language of type theory, which can be easily put in proof assistance, which can hopefully lead to.
Are you there? Like, oh yeah, you got muted.
Hello, hello.
Yeah.
Oh, sorry. Okay, my phone got a call and I accidentally hung up. So
Yeah.
okay, I was gonna finish anyway. So this is my computer. But essentially that notion of proof assistance, uh, that's the goal for find the whole point of finding new foundations for mathematics is so that we can do it in computers. And I
Mm,
do believe that's actually where math is headed towards. You can already do a lot of classical mathematics in Lean Prover. So
mm.
I've been working on formalizing. I've been working on learning stuff in Lean Prover 4. And it's actually quite doable. Most of it is quite doable. It's only when you deal with the really funny higher level structures like category theory that maybe you invoke some of these higher univalence kind of things. But for most of the things that we're interested in now, topology and stuff, it is possible. It just needs a lot of man hours. So it
Mm,
just needs effort. And and I mean the best people to do this is undergrads, because undergraduates, they're not forced to produce new research, so they can essentially spend a lot of time formalizing what they learned in type theory. And the hope
yeah.
is that the future generation of mathematicians, they will all be doing they'll be all quite familiar with Lean Prover and type theory. And we can and hopefully every paper from then on, every math paper will be accompanied by some code, and then we can build math in a more, it's a just giant library, right? There's Lean Prover 4 has this giant math library, and
Yeah.
that's our tower of mathematics that's more rigorous. Yeah. So after all
I
that I mentioned.
I hope there's like something like I don't I would like it if there's like something like ChatGPT where I can just like write down theorems in
Oh yes,
natural
yes.
language and they just convert it to Lean.
Yes, exactly. So AI Lean, um, yeah. So right now we write textbooks in a natural human language, right?
Yeah.
Uh, we write textbooks in natural human language, and that's what we're used to. So some OpenAI actually built essentially a language model that translates between human language, right? Let me find.
Yeah.
So essentially they built a language model that translates between this language, right,
Yeah.
and a proof, or rather a theorem statement. This is a proof, actually, a proof that this thing. So there is moves in AI that actually make the two more convenient as well.
Yeah, because I feel like AI was meant to do these types of things.
Exactly. So that's also something that I'm really interested in, and that's a huge
Yeah,
thing because a lot of this actually is very tedious, and there's actually quite some amount of automation in Lean Prover right now.
yeah,
Um, and that's great because yeah, but in order to work on the automators, there needs to be people who understand there needs to be people who understand um essentially how the proof assistants work as well. So I see myself as somebody who can do that because I'm interested in computer science and AI as well.
yeah.
Yeah, so that hopefully people who are not so interested in computers, like maybe yourself included, you can we hopefully we can make your job easier.
Please, thank you. Yeah,
Yeah, so that is a definitely work in progress. In fact, I really want to replicate this research. It's just that I haven't had the time to. Time is always the limitation. Yeah.
yeah. I mean, this looks important.
Yes, it definitely looks important. Yeah.
But like these days, I feel like it's all very important, but like everyone in every field is gravitating towards computer science related research, and sometimes that can be a bit of a letdown. I mean, what they're doing is definitely helping, but like they just kind of like don't do the things that they like wanted to do initially. Like a lot of the quantum gravity research these days are gravitating towards theoretical quantum computer science. So like I don't know.
Mm,
Um I feel like if the people like work on the pure computer science problems, that would make our lives very easier. But then again, the people that but then like because it's like a new field and there's a lot of low hanging fruit, a lot of
yeah.
people just gravitate towards there. And like a lot of the more aesthetically pleasing things are not being done.
Mm,
So
yeah. Yeah. So anyway, sorry, I gotta go because my parents are waiting for me downstairs. So
okay,
yeah, if not, it's been a fruitful session today. Thanks.
thank you.
Okay, thank you. Bye.
Bye.